September 17, 1948. At the Kapustin Yar test range, preparations were underway for the launch of the R-1 rocket. Chief designer Sergei Korolev was at the launch position, watching over the vehicle intended to become the first ballistic weapon of its type. The atmosphere was incredibly tense, as the project was overseen by the country's top leadership, including Joseph Stalin himself. Failure could mean serious administrative consequences for the program's participants. The rocket was set on the launch pad. Its fuel tanks were loaded with liquid oxygen and ethyl alcohol. The RD-100 engine had to provide 27 tons of thrust to deliver the payload to a distance of 168 miles. After the launch command, the engine ignited, and the rocket began to lift off, gaining speed. However, just seconds into the flight, it lost stability. The vehicle began tumbling uncontrollably, veered off its trajectory, and crashed into the step, resulting in an explosion and total destruction. The first test ended in an accident, followed by a series of technical failures. Subsequent launches were also fruitless. Rockets exploded on the pad, fell shortly after takeoff, or went significantly off course. Out of a batch of 9 rockets in the first series, only 1 reached the target area. 8 vehicles were lost, signaling a critical situation. Leadership and military officials demanded an explanation for the ineffective use of funds and resources allocated to create strategic weapons. To understand the reasons for this, we need to look back at events from 3 years earlier. In May 1945, in the Nordhausen area of Germany, the Peenemünde test sites and V-2 rocket factories were discovered. These ballistic missiles had been used in the final years of the war. A decision was made to study and utilize this technology. Special teams organized the collection and removal of hardware, equipment, and technical documentation. At the same time, a search was conducted for German specialists to bring into the work. Despite the volume of captured material, it turned out that a significant part of the documentation had been destroyed, and what was found was fragmentary. The V-2 samples delivered to the engineers were in poor technical condition. During preparations for testing, numerous defects were found, leaking tanks, and failures in instruments and electrical circuits. The quality of materials proved to be low, with heavy corrosion on metal parts. Rubber seals were losing their properties and falling apart. It became clear that directly copying the foreign design was impossible. On April 14, 1948, a decree was issued to develop the R-1 rocket complex. Sergei Korolev, who had recently returned from imprisonment, was confirmed as chief designer. He was charged with the task of creating a new type of weapon. A group of specialized experts participated in the project. Valentin Glushko led the engine development, while Vladimir Barmin handled the launch equipment. The control systems were developed by Nikolai Pilyugin and Viktor Kuznetsov. Mikhail Yangel was appointed as the project's lead designer. The team was facing a massive engineering challenge. Formally, the R-1 project was conceived as a reproduction of the German V-2 rocket, but the adaptation process ran into a number of technical difficulties. The original design used 86 grades of steel and 59 types of non-ferrous metals. Since many of these weren't produced at local plants or had different specifications, they had to find domestic equivalents and then put them to the test. As a result, the list of materials was streamlined. The number of steel grades was cut to 32 and non-ferrous metals to 21. Swapping out the materials effectively led to the creation of a new design. Work at the Design Bureau was intense. Project leader Korolev demanded high performance from his staff and personally dedicated a significant amount of time to the work process. Every assembly and detail underwent thorough development, with one of the toughest tasks being the provision of anti-corrosion protection. The original rockets were subject to corrosion after just a few months of storage, which didn't meet the new operational standards. The technical specifications required long-term storage and reliable operation across a wide range of climatic conditions, from high temperatures to severe freezing. Specialists developed new protective coatings and introduced non-metallic materials with a longer lifespan, conducting numerous durability tests. The tail section underwent a complete overhaul. The structural frame was reinforced, the mounting scheme for the steering servos was changed, and the connection nodes to the hull were modified. The instrument compartment was also upgraded to house the control system electronics, ensuring the equipment would run smoothly under G-forces, vibration, and temperature fluctuations. Alexei Shcherbakov, serving as first deputy, oversaw the changes to the design, monitoring the accuracy of calculations and technical documentation. Valentin Glushko focused on creating the RD-100 engine. Although the unit was based on the A4 rocket engine, the scope of the changes was significant. The combustion chamber required materials capable of withstanding temperatures of 3,000 degrees, while the fuel pumps and cooling system needed upgrades to operate under high pressure. The first units used engines that replicated the German schematic, using domestic material substitutes. The manufacturing process proved difficult. Some rubber metal parts couldn't be reproduced, so components from captured stocks were used to outfit the first series. The development of the launch complex was conducted under the leadership of Vladimir Barmin. The primary element was a stationary launch table where the rocket was secured prior to launch. The technical requirements demanded a structure resistant to the high temperatures of the exhaust plume and capable of supporting the weight of the fueled rocket without deformation, ensuring it remained strictly vertical. An improved system was designed based on an analysis of the flaws found in the previous German analogues. Tests confirmed the effectiveness of these engineering solutions, and this design was adopted as the foundation for future missile complexes. The control system was developed by a group under the supervision of Nikolai Pilyugin and Viktor Kuznetsov. Functionally, it was intended to ensure target accuracy. The instrument cluster, which included gyroscopes, accelerometers, and steering servos, required high-precision manufacturing. Although the electrical schematic of the V-2 rocket served as the basis, the components underwent significant modernization. The new gyroscopes and computing devices demonstrated higher accuracy and reliability compared to the original samples. The developers viewed these results as substantial progress in this technical field. Significant attention was devoted to telemetry, which was essential for monitoring the rocket's status in flight and figuring out the causes of potential failures. Replacing the equipment used on the A4 rocket, an updated system with an increased number of data transmission channels was introduced. This allowed information from sensors to be broadcast in real time to ground stations for subsequent analysis by specialists. By the summer of 1948, the assembly of the first 9 R-1 rockets was completed at Experimental Plant No. 88. Each unit was a complex technical machine, 14 meters long with a launch mass of 13.5 tons, equipped with a 1-ton warhead. Hundreds of specialists were preparing for flight tests. This stage was viewed as the defining moment for the creation of an independent rocket industry. On September 17, the first launch took place. The rocket was positioned on the launch pad and fueled, after which its systems were checked. Sergei Korolev oversaw the general procedure. Following the countdown command and engine ignition, the rocket lifted off the ground. But after a short period, the flight deviated from the standard program. A failure occurred in the control system, leading to a loss of stability, a crash, and a destruction of the vehicle. Analysis of the telemetry data pointed to a malfunction of the AGB 456 pyrotechnic ignition device. As a result, the engine reached operating mode with a delay, and the automatic systems didn't have time to correct the trajectory. Subsequent launches revealed a number of additional technical problems, including control instrument failures, leaks in fuel lines, and the destruction of structural elements under G-force loads. It became obvious that the rocket needed substantial modification and was not currently ready for service. Upon completion of the first phase of testing, Chief Designer S.P. Korolev held a meeting with the project's leading specialists. The launch statistics, where only 1 out of 9 was successful, demanded a detailed breakdown. Systematic work was organized to analyze the causes of every failure based on the mass of telemetry data obtained, in order to transform them into technical solutions. The main problem was identified as the unreliability of the pyrotechnic ignition, which fired inconsistently, either too early or too late. VP Glushko proposed replacing the pyrotechnics with a liquid ignition device, the principle of which involved injecting self-igniting components into the combustion chamber prior to the main startup to create a stable flame. Implementing this technical solution required the development of new assemblies to ensure a stable launch. After a series of bench tests showed positive results, the new liquid device was integrated into the rocket's design for verification in flight conditions. At the same time, a group under the leadership of VP Barmin carried out a reconstruction of the ground cable network. It was established that a significant portion of the failures was caused by electrical interference, defective connectors, and contact oxidation. The network was refitted using higher quality materials and reinforced protection against external factors. N.I. Pilyogin and V.I. Kuznetsov made changes to the onboard control system equipment. The gyroscopes received a modernized suspension system, and the accuracy of the accelerometers and the reliability of the steering mechanisms were improved. All components underwent testing on vibration stands, as well as in thermal and vacuum chambers, to confirm their operability under various conditions. The computing device algorithm was adjusted based on actual characteristics obtained during the first launches to provide more precise trajectory calculations and rudder control. For the second series of missiles, the specialists at NII 885 developed an improved telemetry system known as the DAWN. The system featured an increased number of data channels, improved sensors, and higher resistance to radio interference. This allowed the engineering team to get a more detailed picture of the rocket's status at all stages of flight. Every parameter was captured by recording equipment for later analysis. By the fall of 1949, a batch of 20 second series rockets had been prepared. 10 units were intended for calibration launches, and another 10 for certification trials. At the Kapustin Yar test site, the infrastructure was prepped, including the modernization of launch pads and the refitting of command posts and tracking stations with new equipment. A large number of personnel were deployed to the steppe to prepare the equipment for the final tests. In September, the trials began. The launch of the first rocket of the second series went according to plan. The engine reached full power on schedule, the control system guided the rocket along the calculated trajectory, and the telemetry transmitted a stable signal. A few minutes later, the warhead reached its target on the range. Subsequent launches also ended successfully. Out of 20 units, 17 completed their mission. The 3 failed launches were analyzed. In one case, the cause was a control instrument failure due to a manufacturing defect. In another, a ruptured fuel line caused by metal fatigue. And in the third, a malfunction of the steering mechanism. The identified problems could be resolved by tightening quality control and acceptance testing without needing structural changes. Military representatives considered the 85% success rate a high figure for a new type of weapon. The project leadership, Korolev in particular, set the goal of absolute reliability. This was driven by the high cost of each unit and the requirement for guaranteed target destruction. After the second phase of testing concluded, a series of experimental efforts began to improve the reliability of all systems. Engineers conducted additional endurance tests on the engine, checking its performance in various modes and during launches under extreme conditions. Glushko supervised the static fire tests. The RD-100 engine demonstrated the ability to withstand multiple startups without any loss of performance. The control system underwent many activation cycles, operating without a glitch. Ground equipment was tested under exposure to high and low temperatures, precipitation, and dust to ensure it would function in any weather conditions. By the end of 1949, the R-1 rocket was considered ready for service. The technical teething problems of the early stage had been eliminated. The design had been brought to the required level of reliability, and the manufacturing process had been perfected. Mass production required the approval of the highest leadership. In November, a delegation of designers, led by Korolev, arrived in Moscow for a meeting at the Kremlin. Test reports, efficiency calculations, and production schedules were prepared for presentation to the military and political leadership. The future development of the R-1 program and the entire rocket industry depended on the decisions made at this meeting. Stalin, who was overseeing the project, expected concrete results. On November 25, 1950, the USSR Council of Ministers approved a decree accepting the R-1 missile and its associated complex of ground equipment into service. This event marked the arrival of the country's first long-range ballistic weapon in its arsenal, with a striking range of up to 186 miles and the ability to penetrate the air defense systems that existed at the time. Once the leadership made the decision, the stage of organizing mass production and training personnel to operate the new machinery began. The capacity of plant number 88 in Podlipki, which had been producing experimental batches, was not enough to meet the demand for serial production. Plant number 586 in Dnipropetrovsk was chosen as the main production site, as it possessed the necessary technical base and skilled workforce. Technical documentation and process charts were transferred there to retool the facilities for missile manufacturing. Mikhail Yangel took charge of organizing the serial production process. The priority task was ensuring strict adherence to technologies, as any deviation from the blueprints could lead to technical failures. Specialized workshops were created at the enterprise for manufacturing hulls, engines, and instruments, and the necessary equipment was purchased. By 1952, the plant was ready to begin serial output. In June 1952, mass production of R-1 missiles started in Dnipropetrovsk. The serial models coming off the line underwent comprehensive quality control. Every unit went through testing on stands where systems, tank sealing, and instrument functionality were checked. Permission to ship to the troops was issued only after the full cycle of inspections was complete. Parallel to missile manufacturing, the production of ground infrastructure was established. Launch tables, fueling units, transport vehicles, and monitoring and measuring equipment, all making up a single operational complex. At the same time, the formation of special-purpose missile units began. The selection of officers and enlisted personnel was conducted with strict requirements for technical education and discipline, which were necessary to maintain complex machinery where operation left no room for error. Technical processes, including fueling and connecting lines, required high precision, since equipment malfunctions or negligence created a risk of emergency situations on the launch pad. Personnel training was conducted according to specialized programs involving profile instructors. A training center was organized at the Kapustin Yar Proving Ground to prepare combat crews. Trainees studied the missile's design, mastered pre-launch preparation procedures, practiced deploying launch positions, and worked through action protocols for various conditions. Significant attention was paid to safety when working with fuel components, liquid oxygen and ethyl alcohol, a mixture that is highly explosive. Personnel were trained to prevent leaks and observe safety precautions. The training launches that followed proceeded routinely. The crews performed the preparation and launch operations, and the warheads reached their targets at the set distance. The military leadership was satisfied with the test results. The army had received a new type of weapon capable of changing the very nature of warfare. These missiles had the ability to strike command posts, communication hubs, troop concentrations, and airfields deep behind enemy lines. It was noted that conventional aviation and artillery couldn't match this weapon's range or the speed of its strike. The designers continued working to perfect the machine, as field operations revealed technical issues. A number of components required simplification to make maintenance easier, and specific instruments needed improved reliability. Work was also underway to speed up the long launch preparation procedure. All these adjustments were incorporated into new production batches, making the design more reliable and simpler. By the mid-1950s, R-1 missiles began entering military service en masse. Dozens of missile battalions were on combat alert, maintaining readiness to strike designated targets. Exercises with live launches were conducted regularly to sharpen the crew's skills. The missile forces received special attention, staffed with trained personnel and modern equipment. Units were deployed across various regions. Launch positions were camouflaged and equipped with protective structures and the means to operate autonomously. Each battalion possessed several missiles, a full set of ground equipment, vehicles, fuel tankers, and power stations. The crews remained in a state of constant readiness. An alarm signal meant immediate deployment and preparing the missiles for launch. Combat application techniques were systematically practiced in the field. Officers tracked the time from receiving the order to launch readiness, working constantly to reduce it. Initially, the preparation process took several hours, but over time, those numbers were improved. The personnel worked like a well-oiled machine. Fueling, connecting cables, system checks, and inputting target coordinates were all performed according to strict regulations that allowed for no deviation. However, missile technology was evolving rapidly. Design bureaus were developing models with longer ranges, higher precision, and better performance. The first ballistic missile, the R-1, was gradually becoming technically obsolete. A range of 168 miles no longer met current requirements, as newer models could hit targets thousands of miles away and carry a more powerful payload. By 1957, the military began gradually phasing out the R-1, replacing it with more modern versions created by the same design team. The experience gained during the development and operation of the R-1 served as the foundation for the family of Soviet ballistic missiles. The engineering staff mastered the design of engines, effective control systems, and durable structures. Military specialists mastered the tactics of missile warfare and trained a cadre of professionals. The last R-1 missiles were removed from their positions, giving way to the next generation of hardware. Operation of this weapon marked the initial stage in the development of the missile industry. The technological solutions implemented by the development team would, a few years later, make the space program a reality, including the launch of the first artificial Earth satellite and putting a man in space.